So first moon bounce was back in 2019. It's the 2 meter single Yagi, the 18 mm Yagi, and with that Yagi, I worked for 2 years until I had to move. I did 51 DXCC entities, and so that was 10 years ago, and I decided I better build another one. And I do want to point out, I think most people know this of me, that my greatest interest is 6 meter EME in terrestrial propagation. So let's talk about what this presentation is about. And what I wanted to do was design a small, effective EME station. So small. What's small, and what do I mean by effective? Well, I think an effective station is a station that can work another small station. So we're not talking about a 4 Yagi station that can work a 3-element beam. I wanted to look at this from the standpoint of a small station that can work another small station. And in this presentation, I want to talk about building, not operating. Operating, a whole nother presentation. It's too much to put into one. Let's talk about some basics. So in 1946, Project Diana detected moon echoes. They thought it was a big deal. Scientists didn't know they could do it until they tried. They pointed a radar array at the moon and picked up the horsepower and were able to detect it. Well, it took until 1953 for the amateurs to get involved. And so 1953, after 3 years of trying, the first 2-meter EME QSO was made off the moon. Well, it took until 1972. We've already walked on the moon. But it took till 1972 to do it on 6 meters. And those 2 stations were 8 6-element Yagis each. So 72. And then in 2003, Joe Taylor comes out with JT65 and he makes it possible to do it with relatively small antennas. Thank you, Joe. So in the world of EME, every decibel counts. The moon's a poor RF reflector. There's huge path losses. The signals are incredibly weak. Noise is abundant, often sub-audible. Little or no margin of error. So a few dBs can take you out of the game, completely. And it's common to try to work a station and not hear them for a very long time. So let's talk about signal to noise. In this radio sky map, that red slash is the Milky Way. It creates a lot of noise. So we have galactic noise, we have sun noise. For a couple of days a month, the sun and the moon are coincide. They're right next to each other or overlapping each other, and the sun makes a lot of noise. And side lobe noise is huge. So you want antennas that have really good pattern, so you're not picking up the side lobe noise. And receivers need noise too. Moon range. So the moon's in an elliptical orbit around it. the earth, and so it's closer and then goes farther away. Well, when it's close, that's 2 dB increase in signal strength. And that's big. That's big for EME. Every decibel counts. Faraday rotation, it's kind of the QSO killer. It's something we have to contend with. It's changing and it's unpredictable. The Earth is spinning and the moon is moving by, and so the angles when it's the atmosphere are changing. So this Faraday rotation is a kind of an unpredictable QSO killer. So what are the losses for Faraday? The lot, because if you were, really at 0 degrees, that's full strength. You go to 90 degrees out of phase, we're talking infinity. But at 45 degrees, we're talking 3 dB a loss. And you go 60 degrees, that's 6 dBs a loss, and that's a lot. So what do you do? What do you do from a design standpoint? One approach is to wait, because things are changing and they'll rotate back. Another one is to use cross-polarized GAGs, and that way you switch them and find the one that's best. Or the other option is a circular polarization, but that comes with a penalty. So if you lose, you get a 3 dB penalty if you go circular polarization. But what bands? That's kind of the first question. You're going to do a system, and I'm kind of thought, well, what bands am I going to do? Well, every band has EME activity starting at 50 megahertz, and they're all there. But the big ones are 144, 432, and 1296. Those are the where you see the most activity. And then I'm going to include 50 megahertz because it's a magical band. So it's in my list of target bands to build a small station. So 6 meters, 2 meters, 70 centimeters, and 23 centimeters. Those are the ones I picked. Okay, I'm going to look at those. So this little nifty chart is all the noise sources. That top curve is all the noise sources added together. So on the left side of the chart, where we have 2 meters and 6 meters, it's dominated by galactic noise and side lobe noise. 432, 1296 are right in a sweet spot. And then above that, the noise is starting to go up again, but it's moon and atmosphere and receiver noise that dominate the higher bands. So let's talk about pros and cons of our target bands, or the target bands I selected. On 6 meter, equipment's readily available. It's technically more forgiving. You've got ground gain to help you. Feed line loss is manageable. You can have the LNA in the shack. You can put your LNA in the shack. So that's a little.
That's me, hang on.
Thank you. Sorry. And 6 meters got other uses too. You've got sporadic EF2, TEP, meter scatter, tropospheric. So it has other uses if you want to go 6 meters. I like it. Cons are they're big antennas, big power needed. You got to hold that stuff up in the air, so the structural requirements are big. It's the high noise band. You have all kinds of noise, galactic side lobe. You have local noise. You get noise. You work on, if you operate 6, you've got local noise. That makes it all the most difficult band. On 2 meters, there's a large group of operators, equipment's readily available. There's other usage for 2 meters. You can do sporadic E and ear scatter, tropo. It's easy to expand 2 meters by adding more Yagis. The cons are, they're still kind of big. Line loss is a little more serious. You still have all of the galactic noise, the side lobe, local, ionospheric, but it's much less than 6. 70 centimeters is 432. Now, lower power is required. The antennas are much smaller. A lot, 432 antenna, a lot smaller than 2 meter antenna. It's easily expandable. There's lots of stations. It gets a little more technical. Equipment's not as readily available as 6 and 2, and the line loss is more critical. Then 23 centimeters for 1296. It's the fastest growing EME band. There's a lot of operators. You can do CW. The antennas are small. They're so small you can make them work. Cons are it gets technically more demanding. Equipment is much more difficult to source, more expensive, specialized equipment. Line loss becomes huge. And it gets harder to get high power. And then you just got to start thinking about your cable connectors because they're bumping up against what they can handle. So, what modes are operated on these bands? 2 and 6 is pretty much digital. On 70, it's digital, but you get some CW. You got a big station. And 23 centimeter, you can see from the graph I got is a fair amount of CW operated on 23 centimeters. But remember, the digital modes allow your antenna system to be smaller, and we're after doing a small station. Or I am. But so there's some design questions, your basic questions. How much gain do I need? Do I need a preamp? Where do I put it? And how much power do I need? What about the feed line? How do I know how big a feed line I need? What are the things I don't know? And I like this chart because it shows it's to scale. So the size of the Earth and the Moon and the distance between the two are to scale. So that's the QSO path that we've got to make. So there's two methods to design a moonbound station. Well, you can go theoretical engineering and get all the formulas. Joe Taylor's done a lot of work on that. Or, because I'm an architect, I don't like empirical engineering. I'll think it's cathedrals for no calculators were used or computers and just trial and error to find out what works. So theoretical engineering tools, what are the tools out there? There's a couple of really good ones. They're free. The K6EME has a lot of variables and a lot of control over the design. The simple calc is a little simpler. It's basically the same thing, but it removes a lot of variables and it makes it a little easier to play with. But they're both analyzing total system loss versus gain and power. So empirical engineering requires historical data. So I went to look at stations that I know that are successful small stations. A lot of them are portable because they have to be small if they're portable. See, you have Lance who does big time 6-meter D expeditions. Gene, he operates portable on 6, 2, 70, and 23 centimeters. I put up my portable station in 2017 and still using it. At Princeton, they did a 2 432 station and did a lot of work on what's half loss and how small can it be. Peter K6EME operates portable with 2 meters, 70 centimeters, and 23 centimeters. I talked to him and asked him, how long does it take to set up? He says he can get it up in 15 minutes. Josh is up in near Santa Rosa, and he's very successful with 4 Yankees, 5 elements, pretty short Yankee, but 4 of them. And then also got to think about the idea of expanding. I wanted to, keep that in mind in the design. Princeton's station there, they had 2 Yankees, and then they did 4. Then they added 2 more and had 4. Peter K6EME, he has a single boom on that tripod, and so the outside connections or brackets that he has are for 2 meters, and the inside ones for 32, so he can convert from 2 to 6. So, what do we learn from all of these stations? Well, I looked at all of the gains and how much power they run, and kind of see where the common denominator comes in. So I came up with 17 dBi would be a good design minimum. Or if you use ground gain on the horizon, you could probably, 14 dBi plus the ground gain will get you there. But what are the other common factors to all of these stations that we talked about? And they all run separate preamp with a low noise figure. Low noise figure is more important than gain. Antennas have good gain over temperature or pattern, so we're not getting big cycles. Low attenuation feed line, and they're all skilled ups. So, Yankee, antenna, or dish. Generally speaking, this is not a hard fast rule, but on 6 meters and 2 meters, you're going to be at Yankee. 70 centimeters, it's kind of a toss up. You could go Yankee or dish, and 23 centimeters and above, it's usually a dish. But you can do Yankees there too. How much power for those 4 target bands that we talked about? 1,000 watts at 6 meters, 500 at 2, 70 centimeters, 250, 23 centimeters, 160 watts. And persistence is the other factor that's required. You can't give up because you failed the first time. So persistence. I like this photograph here. EA8 DB and is a great de-expeditioner on 23 centimeters, and he's put aluminum foil taped on the portable dish And then he wrapped up his feed point with plastic and paper to keep it waterproof. So he also reported that he got an increase out of the aluminum foil, and it seems to hold up very well, he says. He continues to use it. Okay, so my station, 2-meter station, design criteria. I wanted a permanent setup. I wanted to use as much existing equipment as possible. I had some of the parts. I had acquired some secondhand if possible. I wanted to locate the LNA kind of at the base because I didn't want it up in the air where it's hard to get to. And then I wanted to maintain the K6EME 6-foot ladder rule, which is if I can't put it up by myself with a 6-foot ladder, it's not going up. So the plan, the diagram of the plan, so the plan of this was to take the LNA, push it out to the antennas, to the base of the antennas, which requires, some coaxial switching relays out there. Then I run 2 coax, heavy duty, low loss coaxes back to the shack, and everything's in the shack. So I have a transverter and a K4 and a PA, computer, everything back in the shack. But that requires 2 long feed lines. Picking out an antenna. So I look for the low noise, more important than gain. This is Innov antennas. I also wanted, I didn't want to truss it up. So I found the longest, highest gain antenna that I didn't have to truss up because I wanted to keep the construction simple. So 2 of those gave me 17.23 dBi. Okay, well that's what I said it needed to be. So I think it'll work. And then I had to figure out all my losses from the feed point back to the shack and from the feed point to the LNA. And the goal was to no more than a dB. And so I put everything I could, all of the insertion losses, and found out that I needed on my TX feed line, I had to have 1/2-inch helix. And this also helped me decide where to put it because I figured I can only go 50 feet. That's it. Can't go more than that. And still use, my 1/2-inch helix. So then I started building with the antennas built. I had the cuts, phasing lines, everything's got to be in phase. Not that hard, but so I figured out what the length should be and then cut them very carefully, nipped them off, a little bit back until I got to a 1/2 wavelength. And then built a little jig because I wanted every connection point to be exactly the same. So build a little jig, kind of keep it all the same. So it's an integral choke and a single piece of LMR 400 ultraflex. Okay, I need to hold it up in the air. I was able to pick up a US Tower aluminum 16-footer secondhand. That got me up 2 wavelengths, not too bad. I kind of checked out what the gain is at 2. I could go, if I went 9, I get more gain, but also you go higher, you hear more noise. So I figured 2 wavelengths pretty good. And you also have to be careful stacking them. So there's some tools out there for stacking, and I use the BE7 BQH stacking chart and to get it to maximize the gain for stacking. And so I had to build a cross broom. Now, because it's X-pole antennas, so they're both ways, vertical and horizontal, the ends of the center section is aluminum for strength, but the ends are fiberglass too. So making sure that I build it all on the ground. I added aluminum angle so I could have some routing of the phasing lines. And also keep them from getting tangled up in everything, but I did not want to, I wanted them to exit at the rear part of the antenna too, so the feed lines aren't interfering with the pattern of the antennas. And then I maintained my 6-foot lateral because I took it all apart and put it back up on the support structure. Then I tuned them up. I kind of checked them. I found out that the dip was below the band a little bit. So I made some adjustments and got the best SWR at right at 144, 130. That's right where I want to be. That's where 130 is about where all the 2-meter guys hang out. Okay, I have this, I call this the Murphy box. And it's a box that has everything that's most likely to go wrong. So it has the horizontal vertical relay, the transmit and receive relay, it's got isolation relay, it's got termination on the isolation, and then I have the LNAs out there. That's where the LNA lives, and it also switches on for receive and off for transmit. And above the Murphy box is where the power dividers are. Power divider, combiner, the power splitter. So then on the right there, you can see that's the finished array. Not too big. Inside the shack, I needed a transverter because I wanted to use my K4, and I went with the Q5, and the Q5 has an optional internal sequencer, so you can kind of figure out your logic on sequencing all the, you have to sequence your relays, your TX, RX relay, transmit receive relay, the LNA, the isolation relay, all those things, and then finally the transfer is last. So good. I just figured it out what I wanted to do and sent it to them, and then they sent it to me complete. I'm using my old trusty M2 1.2 kilowatt power amp and the wave node watt meter that I already had. Okay, well, final step. I got to put it all on. The goal here is to put everything on the desktop, because if I can put everything on the desktop and not have to flip a switch, turn a knob, or push a button, that means I can remote into my desktop and operate from any place with a laptop. So that window controls the azimuth and elevation of the antennas. I got a couple of windows here. One of them is, I have three amps. I got the HF amp, I have a 6-meter amp and a 2-meter amp, and I can switch them on or off or totally kill the whole 240-volt system, turn it all on. Then the lower panel is a 12-volt switching relays that, because I have a 6 meter LNA, a 2 meter LNA. I have to turn the transverter on and off, and then I have to switch from horizontal to vertical, so I can do that. Got a watt meter for wave node, it's pretty nice. That little window is just the moon footprint, so anything inside the footprint of the moon, I could work. So I get it all done, and then my first code is Italy 2 with AK, who I actually worked 11 years ago. That was kind of fun. Okay, so first day of operating, I worked a 2x9 200 station, 200 watt station. That's less than a twin. So I'm working at stations smaller than I am. But my real prize for the day was auto. Auto has a 7-element, single 7-element gig and 300 watts. On his QRZ site, he has a picture of his antenna where it is at the top. That's the single Yagi. So I worked it. So I figured, okay, it works. So I can work a station that much smaller than I am, then it's an effective station. But man, Murphy shows up. And so I started, I found out that when the manufacturer says that the relays rated for 800 watts, they weren't kidding. And so I blew up the horizontal vertical relay. So I decided I had to go to legal limit vacuum relays. So got those now. And then I was making some adjustment and I broke off this end connector on the power splitter. So I now have new sturdy power splitters. They're not press fit. They kind of have screws in it on the head connectors. Okay, but why not build 23 centimeter EME station 2? Okay. Design criteria was it was portable. And because it's portable, I wanted to be able to power it with 120 volt AC, single 15 amp outlet, because I know I can find that anywhere. Means a lower power PA. It's got to fit in my Ford Explorer. Lightweight, usually doesn't sound like to accomplish that. I got to push everything out to the antenna, so I have really short feed lines, and I don't have losses there. And so I use the IC 905, which is kind of nice because it has a GPS controlled oscillator already. So at 1296, that's really a good thing. And so everything's pushed out to the antenna, and what's running back to the operating station is a Cat6 cable and 120 volt extension cord. So the one way to reduce your feed line losses is to bring a table out to your antenna and put everything on it and operate out there. But Wisconsin winters are cold, and then I didn't want to do that. So what I decided to do was to build a pallet on a rack shelf and put everything on a pallet. So it's got power supplies, 3 of them, sequencer, the TXRX switching, isolation relay, switching for the LNA. It has the power amp, a heat sink that's the size of a toaster, and cooling fans. But the actual little SSPA is not very big. and it's supposed to get 250 watts. So you need a antenna, so the sublunar has a foldable dish, 2.4 meter. I need a sturdy tripod, Paul, IBU, you might recognize that tripod. I need a positioner, and I got, sublunar makes one that weighs 12 pounds. I had to counterbalance it, but my operating station is just a laptop, the control head, and my antenna controller. So then looking at, like I said before, all of a sudden at 1296 or 23 centimeters, everything is critical. You can only get maybe 400 watts out of LMR, 400 Ultraflex. The end connectors are good for about 500 watts. And the relays, the critical thing on the relays, because I'm switching between the PA and the RF unit, and so I'm only switching to 10 watts max, but you need to have a microwave capable relay. That's 3 gigahertz relay is what I got. So bench testing, lots of bench testing, but I found that only needed 4 watts to generate the 250 watts. And then you put all that stuff in a nice gator box and it with easy connectors in the front, and it becomes a pretty small package. And then at the feed point, I'm using a patch feed and a combiner. That there's an isolation relay and a 50 ohm termination and LNA all mounted right at the feed point. So why not run higher power? Well, okay, kind of like version 2.0, a souped up power supply and a different PA that can do up to 600 watts. Things are starting to go crazy. But now I got to be careful to not burn up my coax or go to LMR 600. And now I got my connectors I'm worried about. So it becomes an issue. Okay, so it's done. That's the footprint of the system in my first Q cell on the 23 centimeters. So it's a pretty small footprint to do moon bounce. First day operating 23 centimeters. I worked the twin stations. Yeah, it was pretty good. I worked the regular guys, big stations. I also worked Jonathan, who had a 2.4 meter folding dish, same as mine, and he's running 300 watts. So there's the twin. Because I'm a lunatic, I can't stop. So I'm looking at, I actually have a lightweight septum feed. It should increase gain a little bit in both in transmit and receive. Got one of those on order. Then there's other things, kind of ideas I'm playing around with, but it's kind of an endless rabbit hole. Okay, so what about 6 meter EME? This isn't a plug for Lance. He's going to go to age 40, and he's going to be there from August 8th to August 27th. I don't think at that time of the year there will be any terrestrial propagation to work in. So you're going to have to moon bounce if you want to get H40. So I did a calculation, with Moonsked to find out, because Lance doesn't like to work with when the moon is elevated more than about 45 degrees, because he's got guide wires to hold up his antenna. It's really low to the ground, and it gets difficult for him. So he doesn't like to operate at a higher angle than 45. And if you're a single Yagi horizontal only station, you can probably work up to about 20 degrees. So I did a calculation that he's less than 45, and it's between 0 and 20 degrees for Charlie Mike 97, which is San Jose. I picked San Jose because it's where most people are around here. And I found out that there's one day with low degradation. That's the other point. With low degradation, there's one day for about half an hour that if you're a horizontal only station on the West Coast, that's the best hour. So, and he probably, because I know Lance he'll know that too, so he'll try to work 4. So maybe you get an hour. But August 21st, from 1 to 1:30 UTC, if you have a horizontal only 6-meter antenna, give it a shot. My station's on there. It's pretty basic. But I did a checklist of settings, because working Lance is different. Working 6-meter EME is different, and working Lance at 6-meter EME is a little different. So I did a kind of a checklist that I have here. If anybody's interested in finding out if they could actually work them, or even possibly hear, because that's another way to test your station, is because other people will be calling him, and you can listen in and see if you can hear moon echoes. And on the last note, I'm going to put a plug in for the Fred Fish Memorial Award. It's a big, very audacious goal. But if you're working on 6 meters, you're already started the chase. So you can check your LOTW score and see what you are. There's 488 possible grid squares to work Fredfish. So that's kind of the plug. So with that, I'll take any questions. Yes, John.
One question is, what's an isolation relay? Is that what protects the LNA from the transmitter power because you don't get enough isolation from the TR relay?
Yeah, I'll repeat it for people on Zoom. But the isolation relay, what it does is switches the to a termination or load, dummy load. So it provides isolation, so you don't get any, you don't ruin your LNA by pushing too much power into it. So that isolation relay just switches the LNA out of the circuit during the transmit cycle and puts it on a dummy. Yes.
And early in the presentation, you said that, or at least I think you said that losses were greatest when the moon was closest to you. That's counterintuitive to me.
No, it's 2 dB better.
2 dB better.
Yeah. When the moon is the closest to the Earth. Yeah. Anybody else?
Yeah,
Anybody
so,
think that, they, that they had to be the bigger antennas to do moon bounce? Yeah, you can do it pretty small. Yeah, John, what, you got another one?
Yeah, what's the path loss on 23 centimeters versus 2 meters?
What versus 2 meters?
The path loss or Earth to moon.
200, that's 2 meters, it's 200 and minus 256 dB.
And on 23 centimeters?
Pardon?
23 centimeters is.
Oh, it's, you know, it's weird. The, it changed a little bit by band.
Right.
Yeah, and, it actually, I think goes up a little bit. It's not significant though. But the thing that's cool about the 23 centimeters is, you know, with this, the dish that I have, which is small, a small dish, 2.4 meter dish, you're getting like 26.5 dB gain. Yeah, so it's easy, you can, that's why like on 23 centimeters, it's okay to kind of do circular polarization. You can lose 3 dB because it's easier to get a lot of dB out of it. Where at 6 meters, you're talking really huge antennas to get gain. So the on the dishes, the 23 centimeters and above, you can actually, you know, I found, at least in my limited knowledge, because I don't know if you noticed the date on there, it was May 3rd, it's my first day operating on 23 centimeters. But the signals were so much stronger than like 2 meters, or, you know, 6 meters, of course. Really weak. But it's kind of, that's the advantage to I think the higher bands is that it's easier to get a lot of gain. Anybody else?
yeah, so I have a question. I'm sorry, this is the Summits on the Air operator in me. I want to know, how much does your station weigh?
The 23 centimeter station, how much does it weigh?
Yes,
You know, I haven't weighed all the pieces, but, the antenna is really light. I mean, I pick it up easily with one arm. The tripod's light, the whole, little case that I have, the gator case is easy to pick up with one hand, you know, one arm. It's got an handle on it. And, so that was one of the things about when I was doing the 23 centimeter station. Let's see, I'm gonna exit out of here. Stop sharing, okay. Yeah, it's really light. It's easy to put in a car and move around, and none of the components are very big or very heavy. The antenna itself, the folding dish, I just, I put the tripod up first, and then I just pick it up and put it on, and there's a couple of clamps, and, it's really light. It's a very amazing that how small and light it can be. I find it amazing myself. I think it's crazy that a small station can do that. Anybody else, any questions or wanna, Bill, I see Bill's. WS, do you have any questions? Or you want me I did something wrong?
No.
I would say that the path loss on 23 centimeters is about 270 dB.
That's because of the proximity to the hydrogen line.
I don't know. I don't know why it goes up. It's actually the half loss at 6 is the lowest. And then it kind of gradually kind of goes up, but I can't tell you why.
There's some fancy physics involved, I'm sure.
What do you use to rotate the array and elevate it?
The small, the 23s,
Yeah.
it's actually made by Stealth Lunar, and Stealth Lunar has put together some really good cars, and it makes it easy. And so it's a specialized piece of equipment that he's made to rotate that small antenna. So you just buy it. It's good.
How about two? What are you using on two?
On 2 meters, I have the Alpha Spid L rotator. And I've used one of those for 12 years. They work great. They're really good. They're heavy. They weigh a lot.
They'll be on test. Thank you, Matt.
Okay,
It's wonderful.
thank you.